notice when you see one of those famous pictures of the Earth from space? Probably how blue our planet is. And that's because the ocean covers about 2/3 of the Earth's surface. And in fact, if you spread the water out evenly on the Earth's surface, it would cover a depth of about 2 miles. Yet with so much water on our planet, why has it become such a survival issue for so many cultures, both past and present? Think of the Anasazi of the American Southwest. Think of the Mayans of Central America. Both of those cultures' downfall was due to a prolonged drought. And although not the cause of a downfall, but definitely the cause of a painful period in the 1930s dustfall of the American Midwest. Well, for the very fact that most of the water on the planet is locked up in the oceans, 97% to be exact. And that water is salty and unusable for human use. But does that water remain salty and in the ocean basins? No, it evaporates, becoming part of the atmosphere and then raining back on land, becoming runoff, and travels back to the ocean in the rivers, such as the one behind me, the Olentangy. This video explores the amazing journey a water molecule takes as it cycles through the ocean, the Earth's atmosphere, and then back down to the Earth's surface, either as surface water or groundwater, and sometimes along the way getting ingested by us, animals, and other organisms. So let's explore how a water molecule moves freely and rapidly throughout the Earth's spheres, affecting more than just the water molecule itself. So what drives this process of removing water from the ocean and desalinating it and making it available on land? And does this process happen equally across the globe? And what do these processes have to do with climate? These are all really good questions you or your students might ask. There are 3 videos to this series. The first one covers a hydraulic cycle, this one. The second one will cover groundwater and different types of pollution. And the third one will take a much more local perspective on California's water picture. We'll look at where our water comes from, how we move it around, and how we process it. So we're going to explore different aspects of the water cycle, beginning with looking at the Earth's many spheres, the origins of our oceans. Then we'll delve into the water cycle and we'll look at how that works and how it is different in different parts of the world across different latitudes. Then I want to take a quick look at global change and what that's doing to our water resources. Then we'll look at where water is locked up on our Earth, which are our reservoirs. Traditionally, the Earth can be described as having 4 integrated parts or spheres that interact with each other: the geosphere, hydrosphere, atmosphere, and biosphere. And more recently, another sphere has tentatively been added, the anthrosphere. The geosphere, or the lithosphere, is the solid Earth, which represents the majority of the Earth system, and it includes the crust that we live on, the mantle, the inner and outer core. And most of this is inaccessible, except it's important because it exerts a strong influence on the surface of the Earth, such as in the form of plate tectonics, therefore earthquakes and volcanism. It's where oil is formed, and it's also where aquifers, which hold water, are located. The hydrosphere includes all water on Earth, from oceans to rivers, lakes, groundwater, water vapor in our atmosphere. And this also includes the icy parts of the Earth, including glaciers, sea ice, and ice sheets. And that's called the cryosphere, but it's really a part of the hydrosphere. Next is the atmosphere, which is the mixture of gases that surround Earth, which include nitrogen, oxygen, and many other trace gases. And then the biosphere includes all life on Earth, animals, plants, and other organisms. Clearly, these are concentrated on the surface of the Earth. And plants and animals don't only respond to environmental conditions, but actually exert a very strong control over parts of our planet, especially humans, which is why a 5th sphere has been added, although tentatively, called the anthrosphere, which means the humans and our built world, because we're having such a big impact on all the other spheres. One important reason to view the Earth as a series of interacting systems is because the Earth is not partitioned, it's dynamic. For example, gases don't just stay in our atmosphere. So energy and matter freely move from one sphere to another. So the land, the water, air, and life are all interconnected without boundaries. And keep in mind, energy and matter can move freely from one part of the system to another, but some are very rapid movements and some are much more sluggish and take millions of years. So clearly it's not a smooth cycle time-wise. And we know that what happens in one part of the system can affect other systems. So it's helpful to have a way to describe the effects. So what we're talking about here are the systems being coupled, and these are called feedback loops. A feedback is a mechanism through which the output of a system or part of a system loops around or feeds back into the original system and affects the input into that same system. So we have positive and negative feedbacks, which has nothing to do with good and bad. A positive feedback is one which causes a same direction response. So it tends to amplify the effect of an original change. A negative feedback, on the other hand, is something which causes an opposite direction response and thereby reduces the magnitude of the effect of the change. So negative and positive feedbacks abound in nature, especially in biological systems, and a really simple example is your body. If you exert your body, you overheat. You sweat in reaction to your elevated body temperatures. The sweat dries on your skin and evaporates, which cools your body. So the end result is your body temperature goes down. So that's a negative feedback. And in general, negative feedbacks are a way to maintain equilibrium within systems, especially your body. Positive feedbacks drive a system further from equilibrium and eventually can create runaway systems in which equilibrium cannot be reached no matter what changes are brought about. So I want to give you two examples, both a positive and negative feedback within the water cycle. So the first is we have elevated atmospheric temperatures, which are happening as a result of burning of greenhouse gases. That increases evaporation rates, which increases the amount of water vapor in our atmosphere. And water vapor actually is a greenhouse gas, which traps more solar radiation and increases temperature. So the initial change was an increase in temperature. There was a feedback which drove the system even further from equilibrium and increased that initial temperature. That's a positive feedback. A negative feedback, on the other hand, starts with the same initial change, increase in temperature, that creates more evaporation, which adds more water to the atmosphere, and this results in more low-lying clouds. And low-lying clouds increase the reflectivity of the atmosphere, so when solar radiation hits it, it bounces off, which serves to shade or cool the Earth's surface. So it's clear there are a whole lot of positive and negative feedbacks within one part of this system, and it just generally depends on which one is stronger than the other, as which one would have a bigger impact. Let's turn our attention to the largest water reservoir on Earth, the ocean. The presence of so much water, liquid water on Earth, makes our planet unique and inhabitable. Water and most gases were blown away from the inner planets when the sun ignited. How then did Earth end up with such a large amount of water? Where did it come from to cover 70% of the Earth? To understand this, first let's review our place in the solar system and how that enables liquid water to be present. The Earth has been called the Goldilocks planet. The idea is simple. Let Goldilocks loose in our solar system and she'll choose Earth, since it's just the right distance from the sun to have water. If further away from the sun, water would be in a frozen state, and any closer to the sun, it would evaporate. So it's just right. But that's only half the story. The other half has to do with our atmosphere. Earth has the right atmosphere to warm the planet enough so that water is not frozen. Without our atmosphere, the temperature of the Earth would be negative 18 degrees C. But instead, due to the warming achieved by greenhouse gases, our atmosphere is 15 degrees C. So it is the difference between this negative 18 degrees C and positive 15 degrees C, which is called the greenhouse effect of 33 degrees. And that is why liquid water is able to remain on our planet. But that only explains why water has continued to remain on Earth, but not necessarily where water originally came from. The prevailing hypothesis is that all the water that is now part of the ocean was locked up in magma deep within the Earth's subsurface. And about 4 billion years ago, the Earth began degassing, and volcanism released water vapor and other gases into the atmosphere. And water remained as a gas in the atmosphere until the Earth cooled below about 212 degrees Fahrenheit. At that point, the water vapor condensed, delivering rain and eventually accumulated in ocean basins. So a clear assumption of this idea of the origination of our ocean implies that Earth is not losing nor gaining water to outer space. We're just recycling water around different parts of the Earth. So the water we have is the water we've always had, and it's all the water we will ever have. If that is so, then how can we say we're having a water shortage if we've always had the same amount of water on the Earth? What we really mean is that the water is not in the usable part of our water cycle. And a water cycle is a way to describe the journey that water takes throughout the different spheres of our Earth. So let's explore the path water takes as it migrates through the Earth's sphere. Some of the processes are quite simple and others are quite complex, but they all have profound impacts on weather, climate, life, and in fact our survival. In its 3 phases, solid, liquid, and gas, water ties together the major parts of the Earth's climate system: air, clouds, ocean, lakes, vegetation, snow. And the water cycle shows the continuous movement of water within the Earth and the atmosphere. So it's a complex system that includes many different processes, including evaporation, precipitation, condensation, transportation, runoff, infiltration, among others. Liquid water evaporates into water vapor, condenses to form clouds, then some of the clouds get transported over land, returning as rain or snow back to the Earth's surface. Liquid water then flows across land, becoming either runoff or infiltrates and soaks into the ground. Groundwater then can move into plants. Plants uptake that water, and some of that then gets evaporated from the plants into the atmosphere. That's called transpiration. If not taken up by the biosphere or stored in lakes, some water returns back to the ocean by rivers and streams. Some of it gets stored as groundwater in the subsurface area. So as you can see, all of the Earth's waters are connected, redistributed, all the while getting naturally purified through this process. That's if humans were not part of the picture. That, in a nutshell, is the simplified water cycle. But let's dive deeper into some of the interesting features of this life-giving cycle. Much more water is in storage for long periods of time than is actually moving through this cycle. And obviously the biggest storehouse for water is the oceans. So let's start there, although it's a cycle, so it doesn't really have a beginning and end. Since about 70% of our planet is covered in oceans, evaporation from the ocean accounts for about 80% of all the Earth's evaporation. In fact, 45 inches of water evaporates from the ocean each year. An additional 10% of the evaporation comes from inland water bodies, and the remaining 10% from plant transpiration. The process of evaporation is so great that without precipitation, runoff, and groundwater and discharge from aquifers, oceans would become nearly empty. On a global scale, we know the amount of water evaporating is about the same as the water delivered to the Earth as precipitation, but it does vary geographically though. Evaporation in general is more prevalent over the oceans, while over land, precipitation routinely exceeds evaporation. The highest rate of evaporation from the ocean occurs in winter, both in the northern and southern hemisphere. This might be a little surprising. And this is not due to temperature, but to when storms occur. The location of greatest evaporation is found on the east coast of continents, and this is due primarily to winter storms that move off the east coast of continents, which tend to have strong winds. These winds help carry the water vapor from its source, thereby allowing more evaporation to take place. The other factor is that warm currents tend to move poleward along these east coast of continents, and the cold wintertime air masses move over the water allows for large differences in the air-sea temperature, so evaporation is also enhanced there. Then when these differences in air and temperatures are combined with strong winds, it makes evaporation in these regions very efficient. Yet of all the evaporation that occurs over the ocean, a little over 90% of that moisture falls back into the sea as precipitation. So think about this. After spending about 1,500 years in the ocean, a water molecule takes a journey around the globe and on average then will spend only about 9 or 10 days in the atmosphere before returning to Earth. So as I mentioned, there are very slow and fast parts to this cycle. There is also a close and much more obvious connection between temperature and evaporation. This map that I'm showing you shows evaporation rates across the United States, and you can see that it is enhanced where there's a lot of sunlight and temperatures are high, such as the southwestern U.S. And this is because heat or energy is necessary for evaporation to occur. Energy is used to break the bonds that hold that water molecule together, which is why water easily evaporates at the boiling point, 212 degrees Fahrenheit or 100 degrees C, but evaporates much more slowly at the freezing point. The next step in the water process is condensation, which is the opposite of evaporation. Condensation is the change of water from its gaseous form, water vapor, into liquid water. And this occurs when saturated air is cooled below the dew point, which is really the temperature to which air must be cooled at a constant pressure for it to become fully saturated with water, such as on the outside of a glass of water. So condensation usually occurs in the atmosphere when warm air rises, cools, loses its capacity to hold water vapor, and results in the formation of clouds. So the water cycle is all about storing water and moving water on, in and above the earth. So although the atmosphere may not be a great storehouse of water, it's the superhighway used to move around water. So clouds are, of course, the most visible manifestation of atmospheric water. Even clear air contains water particles that are too small to be seen. And the clouds floating overhead contains ice crystals and small drops of condensed water. These droplets are way too small to fall as precipitation, but they're large enough to form visible clouds. And then clouds are moved from one location to another by global wind patterns, such as the jet stream. And as I mentioned, most water that evaporates from the ocean falls back onto the ocean as precipitation. And only 10% of that evaporation ends up precipitating over land. And this fact helps explain why there's so little fresh water or drinkable water on Earth. So precipitation is the primary mechanism for transporting water from the atmosphere to the surface of the Earth. It can fall in the form of rain or snow. If it's rain, it's precipitation. If it's snow, it's called deposition. So let's turn our attention for a moment to the biosphere. So a typical plant absorbs water from the soil through its roots. The water is then used for metabolic processes. And water then, some of it is eventually released to the atmosphere as water vapor via the plant's stomata. Overall, this uptake of water at the roots, transport of water through the plant tissues, and release of water vapor by leaves is known as transpiration. The process of transpiration has three main roles as far as the plant is concerned. First off, it cools the plants. As water evaporates on the leaves of the plant, energy is released. This process uses energy much like boiling water on your stove, and the energy that is used to do so is taken from the leaf and given to the water molecule as it becomes a gas, whereby cooling the plant. The second role is that it helps uptake of nutrients. The water that enters the root contains dissolved nutrients that are vital to plant growth. Transpiration enhances that nutrient uptake into the plants. The third role that transpiration plays is by helping photosynthesis. When a plant is transpiring, its stromata are open, allowing a gas exchange between the atmosphere and the link. And the open stromata allow water vapor to leave the leaf, but also allow carbon dioxide to enter, which is needed for photosynthesis to operate. Another word that's often used when describing the water cycle is the combination of evaporation and transpiration, which is called evapotranspiration.